Welcome to The Explainer, where today we're breaking down a really fascinating MIT computer science lecture to uncover exactly why the way we log into websites has completely, and I mean entirely, transformed. If you've been online over the past few years, you've definitely noticed that just typing in a password simply isn't cutting it anymore, right? Well, today we're going to dive right into the incredible engineering cat and mouse game that explains how we got from basic passwords to physical security keys and finally to the password-less future we're stepping into right now.
Okay, let's talk about a daily frustration we all know way too well. You know the drill. Frantically scrambling to type in a 6-digit code before that little timer runs out. So why are we doing this? Why on earth are tech companies forcing us to jump through all these annoying security hurdles? Well, it all actually starts with a massive foundational failure of the traditional password. And to really grasp that, we need to look at exactly how computers have historically viewed human authentication over the internet. The absolute fatal flaw of traditional passwords is that they act as something called bearer tokens. Basically, this means whoever holds that secret string perfectly impersonates you. To log in, you are literally giving your entire password directly to a server. And think about the danger there. If you accidentally hand that password to the wrong server, like say a clever phishing site, they can turn right around and use that exact same string to log into the real site as you. It's totally compromised. And this brings us to a really huge human limitation. Believe it or not, the average user's password contains only 10 to 20 bits of true cryptographic randomness. Because we humans are so incredibly predictable, a hacker barely even has to guess to break into your account. Seriously, even if you think you're being clever by swapping an A for an add symbol, 10 to 20 bits means a computer might only need a few thousand tries to guess it perfectly.
So all these vulnerabilities come together to form what we can call the deadly sins of passwords. First, we pick super easily guessable secrets. Second, we reuse them literally everywhere. And third, because they act as bearer tokens, a breach on one single site compromises everything else. This forces servers to maintain these massive, terrifying databases of secrets. And worst of all, trying to block brute force guessing attacks is incredibly difficult without accidentally locking out legitimate users in the process.
So our first major defense against this whole mess was the password manager. The idea here is simple but brilliant. Instead of relying on our flawed, low-entropy human brains to reuse passwords, we replace them with high-entropy, entirely unique cryptographic keys for every single website. Your password manager can effortlessly memorize a massive random gibberish string for Facebook and a totally different, equally massive random string for Amazon.
The MIT lecture we're looking at makes a really profound point about this. It argues that humans simply shouldn't authenticate directly over the internet. We just aren't built for it. Instead, you should only ever use a password or a PIN locally, like just to unlock your physical laptop or your phone. From there, you should let the computer's software do the heavy lifting and handle those complex, unique authentication strings over the actual network. But, this brings up a genuinely terrifying question. If we are trusting our laptops to do all the heavy lifting for us, what happens if malware compromises your device? Think about it. If an attacker hacks your computer, don't they immediately gain access to your unlocked password manager? And by extension, basically every single one of your online accounts? To fix that totally valid compromised device fear, the tech industry escalated things to SMS two-factor authentication. And the logic actually makes a lot of sense. Even if a hacker completely takes over your laptop, they still can't log in unless they also physically hold your mobile phone. The server generates a random challenge, texts it over to your phone, and you manually type it in. It beautifully breaks the reliance on just one single potentially compromised machine. But here is the fatal flaw with that approach, perfectly captured in the lecture. By relying on text messages, you are suddenly deciding that this whole phone network is now fully trusted. You are leaving yourself wide open to an attacker simply calling up a carrier store, pretending to be you, and porting your phone number over to their own SIM card. If they pull that off, they get all your text messages, and your security is instantly shattered. So the big question becomes, how on earth do we prove we have a second device without beaming a highly sensitive secret code across a cellular network that we know we just can't trust? We still need the physical separation of a phone, but absolutely without the risk of someone intercepting a text message.
And the clever answer to that problem is TOTP, or time-based one-time passwords. This is the tech running behind your standard authenticator app. When you first set up your account, you scan a QR code which shares a secret key directly with your phone. Then, and this is the magic part, entirely offline, your phone mathematically combines that secret with the current time to generate a brand new 6-digit code every 30 seconds. Boom! No cellular network required at all.
However, as great as that is, offline generation still doesn't solve the phishing flaw. Why? Because we still have a human in the loop. If an attacker builds a fake Amazon site that looks absolutely identical to the real deal, a confused human will happily check their phone and copy-paste their perfectly valid 30-second code right into the hacker's fake website. The hacker then just turns around and instantly uses that valid code on the real Amazon site before the timer runs out.
Which leads us to a massive, critical turning point in our explainer today. If humans can be tricked into giving away their passwords, and they can be tricked into giving away their authenticator codes, how do we design an authentication system that takes the easily fooled human completely out of the equation? Enter the U2F protocol. You've probably seen these as physical USB security keys. Here's how it works. When a server sends a random challenge to your laptop, instead of you, the human, typing anything, your web browser directly grabs that challenge, attaches the exact website URL to it, and sends it straight into the physical USB key plugged into your machine. The key then mathematically signs that data and sends it back. In this brilliant setup, your web browser actually becomes the hero of the story. A human might glance at facebook.com spelled with a zero and be totally fooled, but your browser isn't stupid. It knows the exact digital origin. So it attaches that fake URL to the challenge. When the physical key signs it, the real Facebook server will look at that signature, realize it was signed for a fake URL, and instantly reject the login. It is practically unphishable. And this also creates a massive bonus for the tech companies running these servers. U2F totally replaces bearer tokens by utilizing public key cryptography. This means servers no longer have to store your private secrets. They only store a public key. If a massive database gets hacked, the attackers walk away with totally useless public keys. Your actual private secrets remain completely locked down and safe on your physical device.
But hold on. How does a server actually know you're using a real, secure key and not some homemade malicious software just pretending to be a USB key? To stop that, the protocol relies on something called device attestation. This is basically a factory-installed certificate inside the hardware itself. It proves to a server, like GitHub or Google, that your key is a legitimate, non-backdoored piece of hardware from a manufacturer they actually trust.
Now, the crucial mechanism here for your privacy is something called a handle. Your physical key actually generates a fresh public-private key pair for every single website you visit. But instead of running out of tiny storage space on the USB stick, it does something super clever. It encrypts the secret key using a master key, hands it over to the server as a handle, and basically lets the server hold it. The server hands it back to you when you try to log in, your device decrypts it, and you get to authenticate without leaving a unified, traceable footprint all over the internet.
Now, this hardware tech is undeniably incredibly secure. But let's ask the practical question staring us right in the face. What if you inevitably lose your little USB stick? Or, what if you just find carrying a clunky dongle around way too cumbersome for everyday life?
Well, let's fast forward to the present day and see how this all evolved into passkeys. The tech industry basically took that unphishable U2F public key cryptography and baked it directly into the secure chips, the TPMs, that are already inside your laptop and your phone. By syncing these credentials across your devices via the cloud and protecting them locally with a simple Face ID scan or a PIN, they've totally removed the need to carry around a physical USB stick. They've effectively made completely passwordless logins a reality for everyday users. So, as we wrap up this explainer on our digital security evolution, I want to leave you with one final thought. Now that you truly understand how easily broken bearer tokens are, the terrifying vulnerabilities of SMS networks, and the absolutely incredible engineering behind public key cryptography, are you finally ready to embrace a passwordless future? Thanks so much for joining me on this deep dive, and hey, keep your digital life secure out there.